video for investigation 4B, which is called thermal advection. And I got some good news for you in this video, and that is that I think relative to some of the other investigations that you've had to deal with during this week, that this one's actually going to be kind of nice. This is going to be a short and sweet video. We only have 3 content slides here, and I don't think it's going to take a whole lot of time to get through this. So this will be a relief after investigations 3A, 3B, and 4A. So why don't we get to it and talk about thermal advection. So I'll start with the PowerPoint. Now, thermal advection is kind of a fancy term for just describing how the wind moves air that has one temperature characteristic to a location that has a different temperature characteristic. So we'll actually deal with thermal advection on a daily basis. It actually sounds tougher than it is. Advection, and this is the actual definition I want you to have, it's a transport by the wind of air with one temperature characteristic to a region that has a different temperature characteristic. So that's a lot of words for a concept that's actually pretty easy. So let's start with the first figure in the investigation. So this is just a schematic of the eastern quarter or so, northeastern quarter of the United States. And these red curves are isotherms. So we have 10, 5, 0, and -5. So this is a winter schematic where obviously it's colder to the north and it's a little bit warmer to the south. So I'm going to define both warm and cold advection. So warm advection is just basically transport of air by the wind of warm air to a region where it's colder. This is basically a really complicated way of saying a south wind. So here is what I've done. I put in this dashed red arrow here, and what you've seen is that the dashed red arrow is basically perpendicular to the isotherm. So assume that this arrow is the wind direction. And so what you see here is that the wind would basically be moving warm air from south to north, which is exactly what you would expect. Warm advection is basically just the transport of warm air to the north by the wind. So you typically see warm advection when the winds are out of the south or they're southerly. Conversely, cold advection is transport by the wind of cold air to a region where the temperatures are warmer. So cold to warm. So here is a blue dashed line that I put in. So again, I've drawn this dashed line, and again, this is not in your investigation. This is just to help you. And you'll see that this blue line, again, perpendicular to the isotherms. And if you assume that this arrow indicates the wind direction, so basically north to south, now what you see is that this north wind is transporting cold air from north to south. And again, this is not a surprise. North winds typically transport colder air from the north to warmer regions that are located in the south. Okay, now, advection itself is typically determined by 3 different controls that can work together, by the way. The first control is the wind angle relative to the isotherms. So this is a map. We again have isotherms on the map going all the way from 15 degrees in the far north to 50 degrees in the far southeast corner here. And in addition to our isotherms, in this particular map, again, northeastern quarter of the United States, we just basically have the wind direction and speed components of stations in this part of the world. And again, it's not real world, it's just a schematic. What I'm going to do is I'm going to circle 2 different locations just to explain to you how wind angle has an impact on advection. So here's our first location. Now what you'll see here is that the wind is perpendicular to the 40-degree isotherm. Now, what I want you to do, instead of just thinking about the wind kind of blowing at this isotherm, is I want you to imagine that you've got some sort of maybe like a whiteboard that's on wheels. We have these in a lot of our classrooms on campus, these big whiteboards that kind of roll around classrooms. So if you imagine pushing against this whiteboard, and your hands on the whiteboard are going to be perpendicular to the whiteboard itself. And so imagine that the wind is your hands and that this isotherm is the whiteboard. Now what will happen if you push on the whiteboard is that the whiteboard will then begin to move so that it basically just is forced by your hands. And so The whiteboard will move to where you're pushing it, and this isotherm will move in the direction that the wind is pushing it, in this case, from south to north. So that is an example of when the wind is perpendicular to an isotherm, and the wind is just basically going to push that warmer air towards the north. Now conversely, you can have a station where the wind is basically parallel to the isotherms. So instead of the wind blowing directly into an isotherm, when it's parallel to the isotherm, let's go back to our whiteboard example where the whiteboard is on wheels. Now instead of pushing against the whiteboard, in this case what you'd be doing is you would just be running your hands along the whiteboard itself, just basically trying to erase the whiteboard with your hands. Now, when you're basically just moving your hands along the whiteboard, parallel to the whiteboard itself doesn't move. And so when the winds are parallel to the isotherms, you actually don't get any advection at all. The wind is not transporting warm air towards the north, nor is it transporting colder air to the south. So you maximize your thermal advection when the winds are perpendicular to the isotherms, and then as the wind angle gets smaller and smaller, the advection decreases until there's no advection when the winds are blowing parallel to the isotherms. So that's the first factor. The second factor has to do with isotherm packing, or what I refer to as the thermal gradient. Now we already talked about pressure gradient in our course, where the pressure gradient is a measure of the rate at which pressure changes over distance. Thermal gradient is very, very similar. Now what we're talking about is the rate at which temperature changes over distance. And we measure thermal gradient basically by just looking at the packing of our isotherms. And just like with the pressure gradient, where the pressure gradient increases as the isobar packing increases, the thermal gradient also increases as the isothermal pattern is packed. And so, but that basically means is that where we have our isotherms really close together, the temperature is changing quickly over distance. And so if the wind is blowing into our isotherms as we have here, that's going to result in a very quick transport of colder air towards the south in this example. So advection increases when our isothermal packing or our thermal gradient increases. Conversely, here, even though we have winds that are perpendicular to our isotherms, the advection is going to be much, much smaller because the distance between our isotherms or our thermal gradient is much, much smaller. So even though we have winds blowing perpendicular to the isotherms, because temperature is changing much more gradually over distance, the rate at which we get our thermal advection, in this case would be warm advection, is going to be really, really small. Okay, so that's thermal packing. Our final factor is wind speed. All right, so basically when the wind is blowing fast, when we have strong winds, then what's going to happen is, assuming that the winds are blowing at a large angle to our isotherms, as we have up here in Minnesota, then what we're going to see is our advection is going to be strong. In better words, this is going to result in a very fast temperature change, these strong winds. So this wind is quickly transporting colder air towards the south. So we have strong, cold advection. On the other hand, at this location, even though our wind is perpendicular to the isotherms, you'll notice that relative to our 50-knot winds in Minnesota, we just had this 5-knot wind over Ohio. Perpendicular to the isotherms, but the winds are much weaker. And so since the winds are blowing much more slowly, the transport, in this case, of warmer air towards the north, warm advection, is going to be much more gradual than it will be than what we're seeing here in Minnesota with this cold advection. So basically, again, these three factors that basically control our advection are wind angle, where advection increases as the wind angle gets closer to 90 degrees, isothermal packing, where the rate of advection increases as our packing of our isotherms or our thermal gradient increases, and wind speed, where again, given all other factors being equal, that the rate at which we get temperature transport from warm to cold or cold to warm will increase as the winds get stronger. Okay, last slide. And this is basically comparing our patterns in summer versus winter. So before I actually go through it, and there's not much here, just again remind yourself that these red curved lines are isotherms, and we have some stations that are plotted on our maps in this northeast quarter of the United States. So summer, you'll see we have temperatures varying from 70 degrees in the far north to 85 degrees in the southwest. And you'll note that our winds are pretty weak on this map, and we have a number of just open circles. Remember that open circles mean that the winds are calm. So the AMS has created a depiction here where we have a lot of calm winds on this map in this summer example. In the winter example, you'll notice that our temperatures vary from 15 degrees in the north to 15 degrees in the southeast, and this is what we had on our previous slide. And again, this is basically the same winds. So basically what I did was I took the slide from slide 2 and I just used the same map over here for our winter example. Now you'll note that there are a couple of differences between summer and winter that are of note. First, during summer, we tend in the mid-latitudes where we live to see smaller thermal gradients. So we don't get really large north-south temperature gradients during the summertime. This is particularly true at night, where you might even see during some nights during the summer where there's less than 5 degrees temperature difference between Minnesota and, say, Louisiana. All right, so our thermal gradients tend to be much smaller in the summer than they are in the winter. In addition, you tend to see weaker winds during the summer than you do in the winter. All right, so when you take these two factors together, smaller thermal gradients and lighter winds during the summer, larger thermal gradients and stronger winds during the winter, we tend to see really weak advection patterns. In better words, thermal advection during the summer tends to be pretty small when you compare it to the winter. And so, again, you take these two factors, small thermal gradients, light winds during the summer, large thermal gradients, strong winds during the winter. The result is that you get, in relative terms, very small thermal advections during the summer relative to what you see during the winter. And believe it or not, that's pretty much all I need to say about investigation 4B to cover what's in your investigation. So I'm going to end this PowerPoint now and go back to our first screen and get ready to end this video. So if you have any questions whatsoever about thermal advection, again, I think this should hopefully be a bit of a relief investigation for you after the past couple of them. But if you have any questions whatsoever, feel free to post your questions to the discussion board or ask me live during my office hours on Zoom Wednesday evenings during the fall from 7:30 to 8:30, Sunday afternoons from 2 to 3. But that's it, that's all. I'm going to end this recording now, post it on YouTube, and I'll put an announcement on Canvas when it's ready for you to view.